Hi, in this lecture we are going to discuss what are the different data types of math coprocessor 8087. In last video we discussed about what are the different functionalities performed by the math coprocessor. It is also called as the floating point coprocessor. As well as we discuss that what is the internal structure of this floating point math coprocessor. Along with that, how it is interface with your main host processor, that is it will support 86 and mainly 88 microprocessor. Now we are going to discuss here, that is what are the different data types it will support while performing the complex mathematical operations. We already know that our main processor can perform the operations related to the simple addition, multiplication, division, etc. But it cannot perform the operation related to scientific calculation, that is having the fractional number of very high as well as the very low. Okay, so we start the lecture. Basically it support the three different kind of data types. First is the binary integer data type, packed BCD data type, and third one the real data type. But finally, internal structure of the 8087 it is designed in a such a way that all the data operands are finally converted into 80-bit temporary real format. So what is the 80-bit temporary real format? We'll discuss in the upcoming slides. So we'll discuss one by one what are the different fits are there in these three kind of data types. First one, that is a binary integer data type. So it is a categorized again into three different parts according to the how many bits are there in the format. First is called as the word format. It has a total 16 bits. First of all, we are going to understand what are the different fields. In binary integer format, it has only two fields. One is the sign field and another is called as the magnitude field. Sign field, it is related to either number is positive or negative. For positive number, this sign bit is 0. For negative number, sign bit is 1. And this is valid for all the data types for 8087. Now coming to the point next, that is called as the magnitude. So magnitude is we are going to represent using 2's complement form. See, why 2's complement? Because there is no facility to write the negative numbers in case of representing in the binary form. So 2's complement of positive number, that is magnitude of the positive number in 2's complement, is as it is. That is how we can represent in the normal way. But the magnitude is changed for the negative numbers. So always, that's why we are representing the magnitude in 2's complement form. So these are the different three formats of the binary integer. One is called as the integer, another is the short integer, and third one is the long integer. They are classified according to the how many bits it will support. 16 bit, it is a word integer. Here I am giving the example, that is a minus 32,768 to 32,767 plus. If the number is of the 32 bit, then the range is change, that is a from minus 2 into 10 to the power 9, this is for sake of understanding, to 2 to the power plus 9. This is called as the double word format. Next is the long integer format called as the chord word format. It will support the 64 bits. Again same here, the number is represented in this fashion, that is minus 9 into 10 to the power 18 to 9 into 10 to the power plus 18. So these are the three formats for the binary integer: word, short and long integer. That is a word format, double word format and chord word format respectively. Okay, next one, that is the packed decimal numbers. So basically the packed decimal numbers, it is your simple decimal number. It has a only three field. One is the sign, integer and fraction. Okay, integer, it is a simple number. Fractional, after decimal point there is a facility to represent the total 72 digits, fractional digits, right? So this is the format of the packed decimal numbers, and it is able to define in the 10 bytes of form, that is 80 bits. Next last format is the real number data types. So again, according to the how many bits we can represent, it is a categorized as a short, long and temporary real. Short means it is 32 bit, that is a double word. Long real means it is a 64 bit, this is called as the chord word. And temporary real, it is 80 bit, it is a 10 bytes. Now here you have to understand the processor, that is 8087, always convert any data types into the temporary or real format. So last black color indicate that the temporary real format. So first, real data type has a different three field. One is the sign field, another is called as the bias exponent field, and third one is called as the significant field. Significant, it is also called as the Mantissa field, right? That is a fractional field. Okay, so first one is the 32 bit, second one is the 64 bit, and third temporary is the 80 bit format. So you can check here, it will support, that is a real number data format is support for very high number as well as very low number. You can look at the 80 bit format. The number is minus 0.34 into 10 to the power minus 4932. 2. Number might be the 1.1 into 10 to the power 4932. So this is the ability of the math coprocessor, that's the representation or calculation of the numbers into this range. Now for sake of understanding, we are going to understand how it will going to convert the any format. We are taking the simple packed decimal number, how it is going to convert it into the temporary real 80 bit format. Okay, but sake of understanding, we are not going to cover the 80 bit format. We are going to study the basically the IEEE. There are the two format, one is called as the 32 format and another is called as the 64-bit format. One is called as the single bit precision format, that is related to 32-bit. Double bit precision format, it means it is a 64. So these are the three fields to convert the number into the temporary uh, real data type format, that is the sine, exponent field and Mantissa field. It is also called as the significant field. Now we are going to understand how it is going to convert, that is any packed number into 32 digit single bit precision format. Here it is a one of the example, that is the first, this is the number 43.625. So first of all we are going to convert this number into the binary form. Everyone know about the binary, how to convert the integer as well as the fractional decimal number into its binary equivalent. So it is a binary equivalent of 43.625. The next part is you have to normalize this number. What is meant by normalization? Normalization of the number is nothing but shifting the binary point until there is a single one to the left side. So initially you can observe the this is the number into 10 2 to the power 0, and after normalizing the number it become 1.0101101 into how many bits you are shifted, so that it becomes the normalized, it is a 2 to the power 5. So here it is a very important to understand what is meant by normalization and what is the 2 to the power, because for next calculation this is the 2 to the power is very important. Now what is the next step? Next step is first of all find out the sine field, right? So our number is 43.625, so it is a positive number, so that's why obviously the sine bit is 0, right? It is only single digit, so that's why it is a single digit 0. Next part, that is how to calculate the exponent field. Now in the 32-bit format the exponent field is 8-bit field. The number of times you are shifted to convert the number into the normalized number, this will give the exponent. In our case 2 to the 5 power 5, that is a 5 is very important. So exponent field is used, actually calculated using the bias calculation. First of all you have to understand what is mean by bias. So for 32-bit format, the 2 to the power exponent bit minus 1, that is a 2 to the power 7 minus 1 is equal to 127. This is the bias calculation. So bias plus what is the 2 to the power, that is 5, it becomes 132. So this 132 if you are converted into the binary equivalent, it gives us the exponent field, that is a binary equivalent of 132. Now before moving to the next part, I would like to tell you about the 64, that is the double precision format. Double precision format, it is nothing but the 64 bit. So what is the exponent calculation, that is a bias calculation for it, that is a 2 to the power, how many bits are there in the exponent field, might be there are the 22 23 bits minus 1, so whatever it may be the calculation is nothing but the bias calculation, and you have to add 2 to the power into it, so it will give us the exponent value, right? Next part, that is Mantissa field. The bit to the right of the binary point called as the Mantissa field. It is also called as the significant field. In our case, there is one point, that is 0 1, a red color field, 0 1 0 1 1 1 0 1. This is nothing but your Mantissa field. But now the Mantissa field, there are the, in our format, these are the 23 bits, right? So right now there are only, I think, 8 bits, 8. Now remaining 0 0 to append, so that it become total 23 bits of Mantissa field. So this is the procedure, right? So finally, the IEEE 32-bit floating point representation, or you can say that the single precision format representation of 43.625 is like this: sign bit 0, these are the 8-bit exponent, and 32-bit Mantissa. So in this way, the processor will always convert the any kind of data type into the this kind of format, that is a sign, exponent, and Mantissa, but in 80-bit. Okay, so I hope everyone understood the different data types supported by the 8087, and how it is converted into the single bit precision format. Here we consider the 32-bit IEEE format. Now it's time to exercise. This is the exercise for you. These are the two examples here I am giving. That is, you have to convert these two examples into the IEEE 32-bit format, 347.625 and another 639.6875. Okay, I pause the video and obtain the answers of these two questions, right? Now this is the solution for the first problem. 347.625, obviously this is a positive number, so sign bit 0. First of all, convert into the binary equivalent. It is a binary equivalent. First is 2 to the power 0. Normalize the number in a such a way that only one, that is a one binary bit is left to the left side. So how many bits we are shifted here? 8 bits shifted. So exponent calculation for 32-bit, the bias is 127 plus how many bit you are shifted, that is 8 bit, so it becomes the 135. So the binary equivalent of 135 is nothing but your exponent field. Now Mantissa field, that is whatever the blue color, in the normalized case I am showing the blue fractional part, is nothing but your Mantissa. But to become the 23 bits, I have to append the some zeros. So after appending the zeros, whatever the obtained number is nothing but the Mantissa field. So finally, if we write 3 field together, it will give us the single precision representation of given number, that is a 347.25. Okay, again this is for another number. The same procedure you have to follow to obtain the sign bit, exponent field, Mantissa field, and finally you have to write down into this 3 field into, that is, if you write the 3 field in a one number, it will give us the IEEE 32-bit format. I hope everyone understood about the how to write down the answer for the different data types of supported by the 8087, and how it is converted into the temporary or real format. Okay, thank you.